Okay, good evening, everybody. I hope everyone's having a wonderful day. So today we're going to be talking about binary search trees. Now, before I can do this, I need to talk about ordered dictionaries. So this is a generalization or actually it's technically a special version of a dictionary. And for most people, we just sort of presumed up to this point that dictionaries are ordered dictionaries, but they don't have to be. But I feel like I need to specify what an ordered dictionary is. So the first thing is that an ordered dictionary is simply a dictionary with records of the form. Remember, we have key, data, or value, pairs. But the thing that makes an ordered dictionary what it is that the keys come from a total order. So what does that mean? All it means is that whenever I give you two keys, I'm able to tell you that one key is equal to another key, that one key is greater than the other key, or that one key is less than another key. So I should be able to determine this. If I can do this with the keys, then I could call it, assuming it has all the dictionary operations that we presume, like get, put, remove, then we could say it's an ordered dictionary. But I must stress that if you're wondering what exactly guarantees that it's a total ordering, well, for example, objects like integers, characters, and strings all are able to achieve this. So most of the time, we've been almost presuming that the keys are like this, but all of those keys have the ability to have this so-called total ordering, or they come from a total order. So usually with an ordered dictionary, we can define all sorts of other operations too, because of the fact that the keys can be ordered from smallest to largest, for example. Is that I could give you operations like smallest, which smallest will return the record with the smallest key. See, it makes sense, right? It makes sense, right? I have some other ones too that I also want to tell you about. So some other operations include come join me. There we go. Sorry, I was coaching the camera. So anyways, some other ones, they also include largest. Largest is one. This is simply where we return the record with the largest key. Predecessor. Now, predecessor and successor are two very interesting ones because they're a little bit different than things that we might normally encounter at first. But we'll see as we explore the topic of binary search trees that it does sometimes make sense to think about these two kinds of operations. In fact, you can think about it in terms of a dictionary as well. Suppose that you have a record with some number, and I want the next smallest or the next largest of that from that given key, which you can do, obviously, with an ordered dictionary. So a predecessor is just simply, if you imagine I was able to list out all the records by their keys, smallest to largest, if I give you k, so suppose that this is like a key value, keep in mind that the key doesn't actually have to exist, is that it's supposed to return the record with the largest key, but that has to be less than k. So it's the one that comes just before the value k. So if you imagine if k was a record in the dictionary, it's the one that comes just before it. Successor is the one that just comes right after it. So it returns the record with the smallest key that is greater than k. So a simple way to implement an ordered dictionary is using something we call like a search table. So all this is just an ordered sequence, and you can think of it just as an array that is sorted by key. So just imagine a sorted array. And you could go through and perform all of the standard operations we talked about, get, put, and remove. You can also, I encourage you to think about some of these other operations, how you would achieve them with a search table. So for example, with get, I can use binary search because all of the records are sorted from smallest to largest in the array, right? I could just simply get the key's value and then I could perform binary search akin to what we talked about earlier on in the course, right? And that's how we could achieve the big O of log n worst case running time. That's kind of nice, right? That's a wonderful thing to have. It's this ability to search over sorted data like this. That's a feature that's really nice. For put and remove, since they are sorted arrays, if I do an insertion into my array, and suppose the array becomes full, or it is full. Sorry, if it is full, what do I have to do? I have to resize the array, right? I might have to make it longer. Likewise, if suppose that it isn't full, if I have to maintain that these records are in sorted order by their keys, I would have to figure out where it's supposed to go. So I would scan through and find the appropriate spot to place it. And when I do this, I need to find the appropriate spot. Then I have to shuffle over all these other elements, right? To make sure there's no gaps in the array. So this shuffling process occurs both in the put and remove. Is that I have to worry about having to shuffle them over, akin to something like insertion sort. You know how insertion sort, you have to shuffle over all the elements? You have to do something like that as well when you insert and remove, right? I have to shuffle them all over. Once I make space or I remove an element, I gotta move over all the other elements, and I may have to shuffle over all the elements. So that's why in these cases you end up with linear times. So this is great for small order dictionaries, right? This will work pretty good, seeing as we have linear operations here, and this is logarithmic. This is especially useful if I have to do a lot of lookups. I have to do a lot of searching using the get operation. This is effective, right? But notice very quickly that if I make this order dictionary very, very big, these linear operations, if suppose I have to search the entire dictionary just to find what I'm looking for, or if I want to do an insertion or a removal, I may have to go through the whole thing. Now, in this case, the searches are great. Suppose that I would like to have a data structure that's able to achieve something like this. I would like to have that. Well, I want to also have the same time complexity for the puts and the removes. That would be wonderful, right? Because we know logarithmic growths are much, much slower than linear growth. So, what I would like to do is I want to think of how I can get something like this sorted kind of property that I have with my array, but extend it so that I could do insertions and removals in a similar time complexity. It's not going to be as simple as that at first, but as we're going to see in the coming weeks, that we're able to actually achieve something like this. So that brings me to talking more about trees. So here we go. So if the answer to most questions at this stage will be something about a tree. So not everyone, I'm just kind of joking around, just to be honest. But the true thing is that we're going to see a lot about trees here. So before I talk about too much, I got to lay out some more terminology about trees so that we can pick up and start trying to use some of these ideas. So we're going to talk first about what a binary tree is. So we talked about what trees are, right? We just talked about that last time. So I'm going to talk about what a binary tree is. So let's talk about what a binary tree is. So it's an ordered tree. It's an ordered tree where the number of children, every node has is at most 2. Hence the binary part is at most 2. And one thing I need to point out is that a child is either labeled the left child or the right child. So we're going to have special names for these two children. If there's two of them that exist, one's going to be called the left child, one's going to be called the right child. If I have one child, then it might be a left child or a right child. If I have no children, I'm a leaf node, right? So the one thing I need to stress is that the left child always comes before the right child. That's the next thing. The left child comes before the right child. So I'm presuming that this is a rooted tree, but you could define binary trees for unrooted trees, trees with no roots. But we'll almost exclusively talking about rooted trees. So for example, I can have this right here. So for example, if I have this tree here, I'll normally draw it so that if I have a left child, it's drawn to the left. If it's a right child, it's to the right. So for example, the node here with 2 in it has no left child, but it has a right child. The node with 9 in it. And 3 here, I'm just going to refer to that as the root in this example. But this is an example of a rooted binary tree. So in this discussion, I'll almost always just presume that the tree is rooted, unless I otherwise state. But I must stress that the properties that we're going to talk about are quite general. Now, there is a very specific kind of binary tree we're going to focus on when we talk about binary search trees. It's what we call a proper binary tree. So this is simply a binary tree. A binary tree where every internal node has exactly 2 children. Has exactly 2 children. So just to reiterate, a proper binary tree is where every internal node has exactly 2 children. So remember, the internal nodes, those are the ones that have at least 1 child. So we're only talking about, for example, this node, that node, this node, and that node. A question, is this binary tree, is it a proper binary tree? No, right? It isn't. For example, the node with the 2 in it has exactly 1 child, right? You know right away that this is not a proper binary tree. Let me draw a picture of one. So, for example, this is not a proper binary tree. However, here's a picture of one that is. So here's a proper binary tree. And suppose this is the root here. Now notice if I look at any one of the internal nodes, like this one, notice it has exactly 2 children. This node has exactly 2 children. So this is a proper binary tree. So are there any questions about the terminology so far? What a binary tree is, or what a proper binary tree is? So remember, it's about the number of children. In particular, sometimes we care about it having exactly 2 children for each internal node. So you can have a pretty broad class of trees that all are these binary trees. We're going to focus primarily on proper binary trees, because proper binary trees have lots of useful properties. And for computer science people, we really like it when trees have lots of fun properties we could grab onto. So, I'm sorry, I'm just getting some really good enjoyment out of this. So, let's head over here. I want to talk about some properties that proper binary trees have. So one thing I just want to remind you while I'm over here. Remember, A is a leaf. A is a leaf node here. So it's not counted in this definition. It's just the internal nodes we care about. But just to remind you, just to be very clear, A is the left child of D. And of course, F would be the right child of D. So this is the right child of D. So remember, each of the internal nodes in a proper binary tree has exactly 2 children. So there's always going to be a left child and a right child. That's one thing that's going to be rather important for us, in at least our discussions here. So let's talk about some properties that proper binary trees have, because we would like to use some lovely, lovely, juicy properties. So let's talk about proper binary trees. So some properties of proper binary trees. So I must stress that these are proper binary trees here. So let's talk about some properties that we have. So the first one I want to point out is I'm going to present each one of these without proof. Some of them I'm going to try to convince you of, but for the sake of time, I'm just going to present them without proving them to you. So the first property that I'll just number them here. The number of leaves in a proper binary tree, the number of leaf nodes, is actually equal to the number of internal nodes plus 1. So if ever you want to know the number of leaves, there's a close relationship the number of leaves has with the number of internal nodes in a proper binary tree. The next one is that the number of leaves is always never going to be more than 2 to the power of the height of the tree. So if I give you a tree that is of height 2, you know that the number of leaves is never going to exceed 4, for example. I'm just going to draw a fun picture just to help us see the next property here. In fact, you can see it in the same picture I'm going to describe here as well. So I'm going to draw a fun picture of a proper binary tree. So let's go one more level down. Okay. So I'm going to be considerate of the level and the number of nodes that I have. So I'm going to look at the level and the number of nodes I have. So at level 0, so we describe the nodes at a given level as based on the number of ancestors it has, right? Its depth. So level 0, this consists of all nodes that have 0 ancestors, namely the root. Level 1 consists of the nodes with exactly 1 ancestor. Those that are in level 2, they have 2 ancestors, right? The ones in level 3 have 3 ancestors. So this is why we call them level 0, level 1, level 2, level 3. It's sometimes helpful for us to see this. Now, if you ask me how many nodes are at each level of this tree, well, at level 0, I have 2 to the power of 0 nodes, which is equal to 1, right? At level 2, I have 2 nodes. This is the same as writing 2 to the power of 1. Well, at level 2, I have 4. There's 2 squared, many nodes. At this level, I have exactly 8, which is 2 cubed. So, the natural question is, how many nodes can be at a given level? So the number of nodes at level I can never be more than 2 to the power of I. Yes, 2 to the power of the height. So this is just me writing height to mean the height of the tree. Now, no worries. So I must stress, like you've seen in my example here, it doesn't have to be that the proper binary tree fills this out completely. What I drew over there as an example is something called a complete binary tree. It's where every node has exactly 2 children. But the thing is, I filled out every level of the tree with the exception of possibly the last level. So this is as many internal nodes I could just cram into a tree with this height. So the last one, this one is a little bit stranger at first. So please bear with me. The fourth one is that log base 2 of the number of leaves is less than or equal to the height. And the height is less than or equal to the number of internal nodes. I must stress that the thing that this is going to be highly relevant for us in about a weekish, this one part here, is that the height is never more than the number of internal nodes in a proper binary tree. So these are some fun properties. Now the question is, what exactly is this thing I've been referring to at the beginning of the lecture as a binary search tree? So now I have everything I need to talk about this. So let's define what a binary search tree is. Why don't we do it over here, okay? It makes things a little bit more fun. Let's head over here. I'm going to define what a binary search tree is. So this is the way I'm going to define it in this course. I must stress that this isn't the only definition of a binary search tree that's out there, but most certainly this is one of the classic ways to define one. It's very natural to describe a binary search tree as a proper binary tree. And if we do, we have lots of lovely properties we can use to talk about them. So we're going to refer to a so-called binary search tree. So let me define what that is. So a binary search tree, which I'm going to abbreviate this as BST, just because writing that over and over again can be quite infuriating for some students' arms. So I'm going to avoid doing that. So a binary search tree, or BST, is a proper binary tree. A proper binary tree storing records in its internal nodes such that each internal node satisfies what I'm going to refer to as the binary search tree property, the BST property. Now, do you recall I was talking about binary search a moment ago? I would like if my trees had a nice structure that reminded me a lot of binary search. Now, if I do things right, as we're going to see as we progress through the course, I might be able to get something that's very much like that, but with a tree. So it has to satisfy this binary search tree property, which is the following. So I'm going to first draw a picture, and then I'll list out what this is. So I'm going to draw a picture here. So imagine I give you some node of value with its key is k. And suppose that there's 2 children with keys k1 and k2. I'm just drawing these triangles to represent that these are subtrees of the nodes that contain k1 and k2 respectively. So these are 2 subtrees. This is just, so there's a whole bunch of stuff that could be happening over here as those 2 subtrees. So what exactly is this about? So the first thing that I want you to notice is that I want to make sure that at every one of the nodes, it has to be that whatever appears in this node's key and its subtree, the key has to be less than k, and everything in the right subtree, so I'll refer to these as the left subtree and the right subtrees respectively, because this is the left child and this is its subtree, and this is the right child and this is its subtree. I'll refer to, I want to ensure that if I look at any node that is rooted at this one and its subtree, it has to be that in K2 has to be bigger than K. So let me write out, so this is a dictionary, so it will not store duplicates. I'm going to address duplicates in a little bit though. So it is coming, it is coming. So let me describe what the BST property is every key in the, actually I'll give it a name. Each internal node U, every key in the left subtree of U is smaller than the key of U. And then every key in the right subtree of U is greater than the key of node U. So if you keep this in mind, I'm going to try to make sure that this tree always maintains this BST property for every single internal node. And the leaf nodes aren't going to store any data in them. So the records are going to be stored in these internal nodes. So you might ask, how exactly are we representing this BST? Whenever I hear BST, I think of some sort of tax, like the burger sales tax or something. I don't know. I'm just having some fun here. Please don't bring in the burger sales tax, please. Burgers are just that amazing. They're just too amazing. Okay? I'm just joking around, okay? Don't give any bright ideas. I'm just having some fun here, okay? It's okay. So we have the BST, so let's talk about how you might implement a binary search tree. And I must stress that there is at least a couple different ways to do so. So depending on which source you go to, some will implement it one way, and another might implement it a different way. But the point is, oh man, that's a terrible tax. Oh, sorry, I'm just losing it. The chat's just got me. The point here is that there's at least a couple different ways that are standard for representing a binary search tree. I'm going to stick with the one that is purest to this definition, but I must stress that you can optimize it further, and I'll point out that there's several sources you'll find out there that use the optimized version of this. So there's a couple standard ways. So I'll present you first the way that I'll be using BSTs in this class. I will tell you up front that maybe on the lab you'll encounter the other way of representing a binary search tree. So just be aware that there's a couple different ways you can implement these. So suppose that I consider the following binary search tree. So you might say, Dan, what is this all about? Well, this is actually the tree I drew. Actually, yeah, it's the one I drew earlier, right? This is the one I drew earlier. So the way it works is that I have a root. So I'm going to be hanging on to some pointer to a node that is going to consist of this node that has this data that's associated with D. So D is the data. And so that'll be some record. I have the root, akin to the implementation I showed you the other day for a generalized tree. And what will happen is I'm going to have it where I'm going to have leaf nodes that have no data in them. They're just going to have no records stored in them. So these leaf nodes, they store no records in them. So this is one way to represent the binary search tree. This is one. I'll refer to this as implementation number 2. This is the one that I'll use with all the algorithms I'm going to present you. So this is just a binary search tree based on that definition. But we'll see when we get to play around with some more examples here. I haven't really said anything about these letters or anything. Suppose that these are just records that maintain the BST property. We'll see some concrete examples in a little bit. So here's another way I could represent it. So the same thing. I can have a root. I can have A, F, E, and J, just like over here. So remember, just to be very clear, remember this is the left child of D. This is the right child of D, just as a reminder. And instead of storing nodes that don't have any data in them, instead I'm just going to have null pointers. Just as the left and the right, they're just going to be assigned null. So I'll just write nil just to keep things short. So for any one that would have been a leaf node in that representation, all of these are just going to be represented as null. So these are a couple standard ways of thinking about the binary search tree. But the thing is there's a natural one-to-one correspondence between these two things. So wherever I have one of these leaf nodes, there's null, right? So I like to think of implementation number 2. So I'll refer to this one as implementation number 1. Implementation number 2, I like to think of it like binary search trees on training wheels, because it gives you a couple of fun things that you could do with them. For example, these leaf nodes, as we're going to see when we get to more complicated tree data structures, they serve as anchors that make it easier to perform some of the more complicated operations we're going to do. When you don't have them, when you're dealing with implementation number 1, you have to be very careful because now you're dealing with null pointers all over the place. So I like to think, when I talk about the algorithms, I'll talk about number 2 because I want to make sure that you have some familiarity with how we manipulate the nodes and how we would represent the tree based on the exact definition I gave over there. So I must stress that wherever you have one of these, you can always represent it like this. And I will tell you up front, I do have a picture of what one of the linked tree representations would look like. So I'm going to, just for the sake of time, I'm going to refer you to the linked tree representation. Is in the notes. So just to give you a flavor for that, for every one of these nodes, you're going to actually, instead of it just being where you have a collection of a whole bunch of children, like a list or something, instead you just simply have it where you could just have it where you have your data, like say if it's D up here, say if I take one of these nodes up here like D and I blow it up, I would have the data, I could have the parent, then I would have a left child, so like this would be whatever the left child is, and this would be the right child. So this would be like the left, and this would be right. But take a look at the picture. I show what this would look like when you put in the attributes for each one. So instead of storing a collection of children, instead you just have an attribute called left and another attribute called right, or left child, right child. So you don't have to have this complicated structure where you have to go through all the children. Instead, you could just have a left one and a right one. It's very simple. So everything I said about implementing that linked-based structure applies here. Just I'm specializing it so that we have a left and a right, as opposed to just a collection of children. So I want to talk briefly about a couple other things. There's pros and cons to each one of these representations. The first one I pointed out with number 1 over there is some of the algorithms become a little bit trickier to implement because you have to watch out for null pointers. That's the first thing. The other thing that is a pro with number one is that we can cut down the amount of space I use because all I'm doing is using null pointers whenever I have my so-called leaf nodes that are in that definition over there. The only confusion comes from the fact that when I think about that representation over there, when I look at A, E, and J, you'd be contemplating and thinking those are leaf nodes, which if you take the most purest approach of looking at what that tree is over there on the furthest right, you'd say that, yes? But it just makes things a little bit complicated with that definition. So you have to easily think about it in a somewhat different way. That's one thing you have to keep in mind. But it is an optimized way of approaching implementation number two. So the biggest drawback with implementation number two is you'll notice that I have all these nodes that I'm not doing anything with them other than they're just leaf nodes, right? So you'll find very often that in practice you'll get rid of these. Instead, you'll try to replace the leaf nodes with those null pointers over there. All the algorithms I'll show you are actually quite easy to translate into that representation. Just you have to be a bit more mindful of null pointers. So wherever cases where I presume there is a leaf node, you'll have to check if it's null or not. So that being said, are there any questions? Any questions about representing a binary search tree? So just think about it as now I have a more specialized tree that now only has a left child and a right child. That's it. Everything else I said just applies the same. The other caveat, of course, is that the internal nodes are going to store records. And all of these ones here, if you actually looked at its attribute here, it would just be null right here. How do you connect it to the other nodes? So that's why I'm asking you to take a look at this picture that's going to be in the notes afterwards. So it will show you a tree just like in the example I gave last class. So it'll actually just be a picture just like what I gave last class for a general tree. I show you what the binary search tree would look like with these left-right attributes all connected together. So that being said, let's proceed. I want to start talking about what we could do with binary search trees. So are there any other questions before I proceed? So which implementation do we prefer? I'm going with number two here because this is based on the definition over here. So whenever I describe the algorithms and what we're doing in class, it's always going to be number two here. I just mentioned number one because some people use number one and I want you to be aware of it. I think maybe in the lab you'll encounter it as well. But I like to make sure you get a broad scope of so that when you say you see another binary search tree out there, some people represent them like this, some people represent them like that. But yeah, the one I labeled here is 2. That's the one we're going to talk about. So all the algorithms are going to reference this one. Wonderful. So let's proceed. So let's start talking about what we could do with a binary search tree. So the first thing is that obviously it's a tree, right? So we could do all sorts of things that we were talking about last class, right? So we could do a tree traversal, for example. In fact, you could do even more than just pre-order and post-order traversals. Because it's a binary search tree, and it has this so-called BST property, we can actually do even more than just pre-order and post-order. Yes, there are left and right. There are left and right attributes for the nodes in number 2. Yeah, so the only difference is that the leaf nodes are present or not present. That's the difference between these two. So the first thing I want to talk about is what we call an in-order traversal. So this is one standard traversal you could do with a binary search tree specifically. So in a binary search tree, it visits all the nodes, and specifically the keys we focus on, in increasing order. So we're going to visit them in increasing order. Okay. So, I'm gonna draw with a binary search tree for us. So I'm gonna get 10, 7 on the left, 13 on the right. For the right child, 13, I'm gonna have its left child be 16, its right child is going to be 16. So these are what their keys are going to be. I'm not gonna worry about the other part of the pair for the records. And I'm just gonna draw in the leaves. 7 is not going to have a record for its right child. It's going to be a leaf. And then I'm going to have 2 as its left child. The left child of 2 is going to be a leaf. Then I'm going to have 3 as its right child. And then I'm going to just simply have the left and the right here be leaf nodes. Okay, so the natural thing, based on what I described here, is that we're going to visit the nodes in increasing order. So, in pre-order, do you remember what we did in pre-order traversal? We visit each one of the nodes. I visit myself first, then I consider all my children, right? In a post-order traversal, I consider all my children first, then I consider myself. I visit myself. In an in-order traversal, the way it works is I go left child first, then me, then the right child. So you're going to always go left, then visit yourself, and then you check the right. And that's really how simple it is. I have the pseudocode for it in the notes, so I'm going to ask you to take a look at that. But here's the neat thing about that, is that it actually, if you take this ordering into consideration, if the binary search tree property is true, so as in it's holding for our binary tree, or a proper binary tree here, what I do is I go left first. I could go left, left. I have nothing here on my left, so I have 2. And then I go to the right. I have nothing to my left. I consider myself. Then I go right. There's nothing there. I come back up. I'm done here. I go to 7. I visit 7 because I've gone to the left already. Then I go right. There's nothing there. I go back up. I visit 10. Then I go right. Now I gotta go left, right? I gotta go left. Nothing here. I visit myself. Then I go right. Then I consider myself for 13 because I've already gone left. Then I go right. Nothing here. Consider myself. Then I go right. Then I'm done here, done here, done here, and I'm done. So, what can you say about the keys here? What can you say about those keys, the way I listed them? Yeah, they're nicely sorted, right? They go in ascending order. Very good. They're sorted. So we started at 10 here. So I did an in-order traversal starting at 10. The rules are just simple. I go left first, so I'm going to do in-order traversal to the left. So I will call what I call BST in order. I call it on the left one if I have a node there. Then I visit. Then I go to my right. I call recursively on the right. So the reason why this is the case is because of the binary search tree property. So isn't this neat? So what I could do is if ever I have a binary search tree, if ever I want to get all the keys in sorted order, I can obtain this very easily by doing an in-order traversal. Is that nice? So you might ask one thing. I promised I was going to address one thing. If you don't mind me just going back 1 second. So we talked about in-order traversal here. Somebody asked me about, okay, what if the tree, is it possible to adapt a binary search tree to have duplicate records in it? Now, of course, a dictionary does not have duplicate records in it, But I want to acknowledge that you can always make binary search trees that have duplicate keys in them. So one thing I will mention, and actually I put it in the notes in the description of this link tree representation. So one thing I do want to acknowledge for you is that if you want to learn more about how you implement it where it has duplicates in it, just take a look at my link tree representation picture, and it's right below that in the notes. So if you want to talk about duplicates, I promised I was going to address that. It basically boils down to two things. If you don't care about the data and you only care about the frequency of the keys, you just have a counter that's stored inside of the nodes. You just have another attribute that stores the multiplicities of how many of them you've encountered or how many you have. If you care about the data, then what you do is you store a collection or a container at that node. So those are a couple standard ways to deal with it. And I must stress that most of these algorithms, the way they work, is that you can also have it so it literally has a node with a duplicate value for its key. But I must stress that the way I've designed them here, it presumes they're all unique. But they're very flexible. That's the first thing I need to point out. But I just felt like I needed to acknowledge that because I didn't get a chance to, I was going to mention it a moment ago, but I know somebody brought it up. So I want to acknowledge that for you. So I talked about an inorder traversal. You might ask, okay, so what exactly are the other traversals like on a binary search tree? So this is what the inorder traversal gives me. So let's talk about the different ordering. So we got pre-order, right? We have pre-order. So does anybody have any ideas what the pre-order traversal would be here? And I only care about the keys. So don't tell me what these leaf nodes tell me. They'll just have null in them. But I don't care about those. So what would be the pre-order traversal of this tree here? I'm only going to care about the keys. So I'll start writing. Let's see, you got 10. So remember, I consider myself, then I consider my children. Now, in a binary search tree, always consider left before right. That's just the way a binary tree works. So I go left first, so I have 7. I remember I visit myself first before my children. I go left, that's a 2. I have a leaf on my left, then I go right. I consider the 3. I have just 2 leaf nodes, nothing interesting, right? So then I work my way back up because I'm done with all of those. Then I am next going to consider, I visit 13 next. Then I go to 11 because I go left first before right. And then I have 16. Yeah, 10, 7, 2, 3, 13, 11. Okay, good. I always like to bug you guys. Okay, how about the post-order traversal? Is somebody else working out that? So visit is actually popping it off with the call stack? No. What visit does in the pseudocode, like for pre-order and post-order, it's just a placeholder for us doing some operation or something at the node itself. So it's just to dictate that I am visiting at that time that node. So it's just telling me what order the traversal is occurring at. So it has nothing to do with the call stack. The call stack has to do with the recursive calls. So post order. So we know right away, remember, we're going to start, it will work our way down to 3 first. Because I go left, but I go all the way down. And then I start working my way up from 3. I got 2, 7. And now I've considered my left subtree for 10, right? Then I go to the right subtree. I work my way down. I know I'm going to have 11, right? Then before I can consider 13, I have to go to 16. Then I go 13 and then 10. Very good. Very good. Awesome. Awesome. So we got 13. So let's see what we got here. So we've got 3, 2, 7, 11, 16, 13, 10. Okay. So just remember, in post-order traversal, we visit ourselves last. So remember the order. It's just, You visit your children first, but in a binary search tree, we always go left, then right. So we will recursively call post order on left, and then recursively post order on the right. And then, that's okay, it's okay. And then we visit ourselves after that. Now, there's another kind of traversal I want to acknowledge. I have more details about it in the notes. It's called level order traversal. It's called a level order traversal. So I'm not going to define it here, but I'm just going to give you the idea of how it works. So it's in the notes. I want you to read it. It's another useful traversal. And the way it works is that you use a queue. And the whole idea with the level order traversal is I would like to visit the nodes in the order level by level from top to bottom, left to right. So a level order traversal will go through each one of the nodes level by level. So it starts at level 0, then it goes to level 1, then level 2, then level 3, then level 4. So the way this is accomplished is using a queue, believe it or not. So what you would do is you would start off by building an empty queue, and then you would enqueue in this node, and then what you would do is you would examine its left and then its right, and you would enqueue these, and you'd keep repeating this process by dequeuing the next node out of the queue until it's empty. So this is done with a queue, and the level order traversal here would be, let's see, we got 10, 7, 13, 2, 11, 16, and 3. So these are some traversals. We've talked about a couple of these already, but you can traverse through a binary search tree just like any old tree, but because of the ordering of the keys, we have nice properties we can work with. The in-order traversal is the one that has easily the most interesting one for the binary search tree. So for example, if I maintain all my data in a binary search tree, if I do an in-order traversal, I can guarantee you the in-order traversal will give me all of the records in the order from smallest to largest. So you can even look at a binary search tree as a way I could sort the data. Yeah, that's the thing. Level order traversal, like that's why I said just take a look at the notes. I give how you do it in the notes. It's really simple. Yeah, you just read it level by level. That's all it is. Okay, so how do you go into in order and how do you calculate? So remember, in order traversal, I go left first. So if you look at the pseudocode, what will happen is I will check to see if there's a node for my left child that is an internal node, or just a node just generally is present there. Then I visit myself after I'm done doing my recursive call on the left child. So I'll have a recursive call that happens on the left child if it exists. And then after I come back from processing that recursively, because remember, I'm just handing off all that work to somebody else to do. That'll be some other recursive call of in order that is just going to be simply taking care of the left, and then I go to myself after I receive that, and then I go right. It's just left, myself, right. That's it. It starts at the root, just like a pre-order or a post-order, because we only have access to the root, right? Remember in our representation, we just have the root. Just like if we have a linked list, I only have access to the head, at least classically speaking. It's the same idea. So are there any other questions? But I want you to take a look in the pseudocode in the notes after class. I have more details there. So the big thing I just want you to be aware of is that it gives you them in sorted order. So you can look at a binary search tree as a way to sort data, for example. That's another thing you can think about. So the next thing I want to talk about is, in fact, how we can do some of these operations. So I thought I would start off with something distinctly related to an ordered dictionary. I'm going to start off with something I would argue is kind of simpler. I'm going to start off with the smallest operation. And I don't mean like the smallest operation. I mean the operation called smallest. So I'm going to sort of build up a repertoire or collection of operations, and some of these algorithms are going to depend on them. So you're going to see I'm going to start off with some rather simple ones, and then it's going to really start building up to something a little bit more tricky. But I don't think they're necessarily too tricky. So let's start off with smallest. So remember, the operations, the goal here is to end up with the the data or value. Or in our case, I'm going to give you the node. I would like to know what the node is that has the smallest key in it. So the one thing I want to point out, if you looked at my binary search tree over there, where was the node with the smallest key? Where was it? Was it like furthest to the right in the tree? Was it like in the root? Where was it? So you know you're going to have to go left, right? So you know that will always get you a key that's less, right? So what node actually contains the one with the smallest key? So any ideas? I already see left child in the chat. So if I were to draw out a binary search tree, where would it be? Yeah, it's the left deepest internal node. Yes, exactly. So notice that the smallest key is in the leftmost internal node. So all we need to do is just keep going left as far as we can, right? And I'm just going to keep going as left as far as I can until I hit a leaf node. Because I can guarantee the leaf node exists because it's a proper binary tree. So here we go. So here's the algorithm. So all I'm going to do is I'm going to give you smallest. So it's called smallest. I'm going to presume that the smallest operation gives me a node that is the root. So I must stress that the root is just some pointer to some node. So sometimes if you want to compute the node with the smallest key in it, I could just simply call it upon any one of the nodes in the tree, and it will get me that smallest key of a node of that given subtree rooted at R, that whatever that node might be. So it's going to be a root R of a binary search tree. And as output, so what I'm going to return is a node storing the smallest key. You might ask, why am I returning the node? Because at the beginning I defined it as returning the data, the record, right? I'm going to be using this to build some more complicated algorithms later. So I'm going to give it to you this way, and it's very easy to modify it to have that behavior. So I'm just going to present it this way, like I'm going to present some of the other operations you're familiar with in this way. They're very easy to modify to get them to behave exactly like the ADT. I'm just giving them this way so we could wrap it all in a nice bow, and I could use some of these algorithms elsewhere, because we would like to be able to reuse some of the algorithms that I'm providing here. So a node storing the smallest key, or null, if the tree has no data in it. So this brings me to one remark I do need to make. You know how I told you about two different representations of the binary search tree, implementation-wise? So I talked about implementation 1 and 2. In implementation 1, when you create an empty binary tree, the root is just simply assigned to be null. In implementation number 2, an empty binary tree is just simply going to be a leaf node. So it's just going to be a single leaf node, like this. It has no data in it. So just to mention that this is what it will look like for either of those cases when it's empty. So just keep this in mind. So here we go. So if R is a leaf, so if I check if it's a leaf, then I'm going to return null. So I return null if it's a leaf. Otherwise, I know I got at least something. So I'm going to assign P to be R. So there is just a space and not null. So just to be clear, if in our representation, we're always going to be talking about implementation number 2 here. If the tree is empty, it'll just have a single node that doesn't have any record in it. So it's just going to have it'll just have null as its data. So if I ever just want to check it, I'll know right away because it won't have any children. So otherwise, I'm going to assign whatever R is to be P. And I'm going to use the tree almost like a linked list. So I'm going to traverse through the tree just like if it was a linked list, but I'm just going to go as far left as possible. So you're going to see it's going to be very similar to traversing through a linked list, except I don't want to go all the way to the end of it. So watch this. I'm just going to go while P is an internal node. We're going to do the following. So I'm just going to assign P to be the left child of P. So I'm just going to get its left child, and I'm just going to reassign that to be P. Now, you might ask, okay, so what's going on here? So suppose I have some tree, there's some subtree here, and I have a whole bunch of nodes here. Eventually, there's going to be some leaf node here. All of these might have some more stuff going on. So the idea is that R is right here. I assign this to be P, but then what happens is I update P to always be the left child of each one of these, right? So I keep going until P is no longer an internal node. So I just keep going until P is not an internal node anymore. So that means that P, when I exit this while loop, is it still an internal node, or what is it? What is it? It's a leaf. It's a leaf. So right now it's a leaf node. How do I get the smallest record then? So the node that has the smallest record. So remember the tree has a parent-child relationship, right? It's right here. That's the one I want. I want this node right here. So which node do I want of P? Which one is it? Because remember, yeah, so we go all the way down to the left, but if P is right here, and I want the node that's in this box, what is this? What is that? It's an internal node, but it's its parent, exactly. It's the parent. It's the parent. So I just return the parent of P. So I just return the parent of P, which I have access to. So, boom, there we go. So all I do is I go all the way down the left, and then I just get its parent at the end. So you might ask, okay, so what's going on with the analysis here? So I'm going to label some lines here to make this a little easier. You're going to find that a lot of these algorithms have a very similar kind of structure to them. So I have 1, 2, 3, 4, and 5. So 1, 2, and 5. So 1, 2, and 5. These all take some constant number of operations, right? All of these. They take some constant number of operations. We'll call it C1. So now we got to deal with whatever this is. So we know that line 4, this is going to take some C2 many operations, right? some constant number of operations to get the left child. I have direct access to it. So now the real question is what's going on with this? So we have the number of iterations of times C2 of this plus C1, right? So let's put this all together now. So we got to figure out what's going on with this number of iterations. So let's head over here and let's do the analysis. Let's figure out what's going on. So remember, in the worst case, it might be the case that we're going to have to go always have to go all the way down the left, right? But that might mean I have to go through a lot of nodes, right? But here's the great thing, is that we know a lot about proper binary trees. So why don't we try using some of the concepts that we've been seeing with trees? So let's try applying some of these things. So let's talk about the time complexity here. So the number of iterations, for some reason I just can't write iterations tonight for some reason. It's just kind of funny. The number of iterations of the while loop is at most, well, what is it at most? Remember my picture, I go all the way down to the left. I keep going down the left. I keep going all the way. So you know that I'm gonna have to do as many possible leftmost branches. If you think of it like I could branch either go left or I could branch to go right. Think of it like a fork in the road, where I can either take the lovely, pleasant route or the scary, scary right path. And I keep going down. Yes, I see something very interesting in the chat, and I will touch upon it. I really like this. That's where I'm going with this. So is at most the number of nodes in the leftmost branch. Which, if you think of it, we start at the top, right? And I go all the way down to a leaf. It's possible that I might actually be going all the way down to the deepest node in the tree, right? But remember, I start at the top and I work my way down all the way down to the leaf. So it's possible that I might have it where I start off at the top and then I work my way down. And I've seen that somebody brought up a very interesting idea here. Thinking about the height of the tree. So it's no more than the height plus 1. I include the plus 1 because we start at the very top. And do you remember what I told you about the number of levels? The number of levels is always one higher than the height, right? So I go from height level 0 all the way down to the deepest one, which dictates the height, right? So that's where the plus 1 comes from. Thus, the time complexity is C1 plus C2 times the height plus 1, which is, of course, big O of the height. So it seems that the height plays a very important role in the execution of this algorithm. I do have a quick question. What can height be at most, though? Like if I were to tell you the most pessimistic thinking thing you could think about a binary search tree, just imagine drawing one out, and you imagine it looked kind of like my picture over there, but I eliminated all the possible subtrees off to the right. It might represent something very closely related to the number of edges, and in fact, it might be even closely related to the number of nodes. So it might be the case that this height might be something closer to something like big O of n. It might not be big O of n, like n exactly, but it'll be something relating to the number of nodes. Which can be quite, that's not really what we would like to have, right? But I gotta still talk about this at some point. We're working to it. So let's talk about one more operation today. We're gonna talk about get. To perform get, use the total ordering. Use the total ordering on the keys. Use the total ordering on the keys to decide which branch, left or right, to follow. So this is really where the binary search tree sort of shines. And it should remind you of something along the lines, yes, I'll address that after class, but yes, that's correct. So if we think about this is really where the binary search tree could shine. So do you remember when we talked about binary search? Remember how we had it where we would discard 1/2 of the array every single time and we would go to the right half or the left half? We're going to see a mimicry of this idea here, where it's not going to be exactly like that always, but it most certainly is of a very similar idea, because we know how we could search very fast with using binary search like this, right? So I want to try to use or adapt this idea. So just to do an example with you, actually I'll do 2 examples. So I'm going to draw out a binary search tree. I'll go 10 is the root, 7, 13. In fact, I'll read it off in a level order manner. That way, because you know what a level order traversal is. So it's 10, 7, 13, 2, a leaf node, 11, 16, a leaf node, 3, leaf node, a leaf node, a leaf node, a leaf node, and then I just have 2 leaf nodes. So, suppose I did a get operation. If I go get on 10. Actually, let's do get 11. That's way more interesting. Okay, if I do get 11, I start off at the root. So I start up here. Suppose I want to get from the root here. So I start at the root. And do I go left or right? So remember, use the binary search tree property here carefully. Do I go left or right? Go right. So notice that if I go right, I know every one of the keys in the right subtree is going to be bigger than 10. But notice I could do this. I know this because 11 is greater than 10, right? Now, should I go left or right? Left, right? Because 11 is less than 13. And then look, there it is. Is that nice? So I found it. So how do you know I don't find it? So what kind of node do I encounter if I fail to find a record with the key that I want? A leaf, exactly. It's if I, for example, if I did, let's go get 12. So 12, it would make me go this way, then back it down here, then I would hit a leaf right here. If I did get 12, so we know that nothing will be found when I do get 12 because I would go to the right on 11, I would hit a leaf node. Exactly. So let's see, I'm looking at the time here, and if you give me 2 minutes, I could write the pseudocode up. Or would we like to rather stop here? I'm happy to stop here. Either one is okay by me. Okay, I'll just finish this up, I'll finish this up. I'm not going to waste too much more of your time, okay? I just like to make sure I ask before I do things like this. Great. I'll just finish this up. So I'll write up the pseudocode, and I'll just tell you what the time complexity is. And that way, when we come back, we can start talking about the put operation. Okay, so let's proceed. So let's describe the algorithm. So I do get. I'm going to imagine I get 2 parameters here. Like I said, you can easily use this get with a driver function that just takes in the key. Just like what I talked about before when we talked about driver functions for something like a merge sort or a quick sort. So I'm going to have it with where I get a node and I have this key. So as input, I'm going to give you the root R. And I'm going to have a key K. And in particular here, I'm going to be interested in getting the node with that record in it, with the one with key K. Like I said, I'm sort of building up a toolkit for us to use so we could reuse them. But all of them can be easily modified to have the purest of behavior of the ordered dictionary ADT. So it's going to be a node storing key K, or a leaf. So it's going to return either the node storing key K or a leaf where K should have been. So for example, you notice in my example there, I say for instance, when I did get 12, I hit a leaf node. So the leaf node that I'm talking about here, that's the one that I'm referring to over here. So the leaf node I touched upon there, that's the one I'm returning. Is that clear, everybody? So when the fail search happens, I hit a leaf node. I want that leaf node. I might use it for something later on in next class. So I'm going to first check if R is a leaf. So if R is a leaf, then we're going to return R. Because remember, we are a leaf. It's possible that I could just give you a node and I'm just, boom, I'm the leaf. And if I'm a leaf, then I know I better return myself, okay? Otherwise, I check if K equals the key stored in R. So first I check if that is the case. So I see if the key matches K. If that is the case, I found a match. So I'm going to return this node. And you're going to see that this is going to remind you a lot of binary search. You know how I wrote out the recursive version of binary search? It's going to remind you a lot of it. That's why I really want to show this to you right now. So, hence tying all this lecture nicely together. So else if K is less than the key stored in R, then you know right away we're going to be going left, right? So I return get, where I use the left child of R, and I pass along K too. Otherwise, I'm just going to simply return whatever get gives me if I use the right child. So let me just wrap that up. So that's the pseudocode for get. And yes, so just like in binary search, you'll notice that there's at most one recursive call that's going to happen here. So if you ignore the recursion first, you would analyze this and you see very quickly that all of these steps, if you ignore the recursion, it all takes some constant number of steps. But now, what happens is I do at most one recursive call, but how many calls can happen at most? Well, it's going to be the same thing that we had with smallest. It's going to be that it's the height plus 1 at most many calls that happen. The initial call, and then imagine I go all the way down and suppose I get to a deepest node in the tree, which is the height. It'll be sitting at the level of height plus 1. So that means that the time complexity for this one as well is big O of the height. You're going to see that this height plays a very important role. So I have the explanation for this if you want to go back to what I just explained in the notes. So I'm going to stop right here. We're going to come back and we'll start talking about the remainder of our operations. And then from there, we'll see if we start talking about what we could do beyond there with binary search trees. So I say thank you very much. And I apologize again for using some of your time. And I thank you for your appreciation for letting me have it. So I'll say thank you very much and have yourself a beautiful evening. I'll see you later.